Hello everyone. Today we'll discuss about one of the most important topic and frequently asked question from the enzymology, that is the factors influencing the enzymal activity. Part 1. First of all, which are the factors actually influencing the enzymal activity? These are, first of all, the effect of enzyme concentration, effect of substrate concentration, effect of product concentration, temperature, pH, presence of activators or inhibitors, presence of repressor or depressor, and the covalent modification. Now before going in detail about the factors, first let's discuss about some of the most important theories given by some scientists. First is the Michaelis-Menten theory, also known as the enzyme substrate complex theory. Now according to this theory, the enzyme actually combines with the substrate to form an enzyme substrate complex, okay, and which ultimately breaks down to the enzyme and the product at the end. So this is the very important equation given by the Michaelis-Menten theory. Velocity is equal to Vmax into substrate upon Km value plus substrate. Now very important example of this Michaelis-Menten theory is the alkaline phosphatase enzyme. Now you may know that this enzyme actually hydrolyzes the phosphate ester bonds including the glucose 6-phosphate substrate. Okay, it can act on this particular substrate and can break down the phosphate ester bond in this. Now you should know that the alkaline phosphatase has active center, and in that active center it has serine residue. So it will do the following reactions, that is the E-serine OH. That means you will know that the serine is actually the hydroxyl containing amino acid. Okay, so enzyme serine OH will react with the glucose 6-phosphate. So what will happen? Enzyme substrate complex will form, that is a E-serine O and P, and the glucose will form. This will actually undergo breakdown and will form the E-serine OH, means the enzyme, we got the enzyme back again just like the previous one, and the phosphate group. Now, and this phosphate group will be released from this E-serine OH. So at the end, this overall reaction is G6P will convert it into glucose and phosphate, and the enzyme will get back from this particular reaction as we were having before, E-serine OH, E-serine OH. So in short, according to Michaelis-Menten theory, the enzyme, whatever we are having in the beginning, will get that at end after the particular reaction ends. Okay, and we will get the particular product after the enzyme substrate complex process. Now next is the Fischer's template theory, also known as the lock and key theory. Now if you know, in the lock and key, for a particular lock, we have particular key only that actually fits into the complementary shape of the particular lock. The same thing happens with the enzyme. Now according to this theory, the three-dimensional structure of the active site of the enzyme, this three-dimensional structure of the complementary site of this is complementary to the substrate. And so the enzyme and substrate will fit with each other and will form the ES complex. And remember that the substrate fit on the enzyme similar like the lock and key according to this theory. And the lock can be opened only by specific keys only. Okay, but remember this theory is not fully true because this theory couldn't explain the flexibility shown by the enzyme, and this particular flexibility of the enzyme is shown by the Koshland in its Koshland induced fit theory. Now according to this theory, the particular enzyme actually changes its conformational shape when a particular substrate actually gets bind to that or its active site. Now just for better understanding, take an example of the gloves. Now what happens is, at first the gloves is in partially folded position and not in a particular perfect shape of the hand, right, when you are not wearing it, but hand can enter into it, and after the entering of the hand, the particular gloves take its particular hand shape structure, right. The same thing happens over here. When the enzyme is not binded with the substrate, it is actually having a different shape of the active site, but when the particular substrate of this particular enzyme will bind to it, it will change its conformational shape and will particular bind to this substrate. You may think that when a particular different substrate, not this one but particular different substrate having the same structure as that of this substrate, okay, but having different function, so can it bind to this particular enzyme? So the answer is no. It can bind, but the conformational change or the particular shape won't be taken by this particular enzyme because the enzyme is different, because there is a particular substrate analog, and so because the reaction will not occur afterwards. So particular substrate only can bind to a particular enzyme and will form the ES complex. Now remember, allosteric regulation can also be explained by the hypothesis of the Koshland. Now we will discuss about the factors influencing the enzymal activity. First of all, the effect of enzyme concentration. Remember that the rate of reaction or velocity is directly proportional to the enzymal concentration when sufficient substrate is present. Now remember, this property is made use in determining the level of particular enzyme in plasma, serum or tissue. How? Okay, this is done by the endpoint method. In the endpoint method, what occurs is known volume of serum is incubated with substrate for a fixed time. Then reaction is stopped and product is quantitated. And the whatever product we will get is of course will be directly proportional to the amount of enzymes in that particular reaction. Why? Because if we have unlimited amount of substrate in particular reaction, okay, but the amount of enzyme is limited. So of course the particular product we will get will be equal to the enzymes amount only and not the substrate. Okay, so whatever product we will get that will be equivalent to the amount of enzymes in a particular reaction. And so because the velocity is directly proportional to the concentration of enzyme, the graph of the enzyme velocity and the enzyme concentration is a straight line. As this increases, this will also increase. Okay, it will be a straight line. So just remember, whatever amount of substrate is present in a particular reaction, the amount of product always depends on the amount of enzyme or the concentration of enzyme. Now effect of substrate concentration. Now as the substrate concentration increases, the velocities also increase in the initial phase, but the curve after that flattens away. Why? Because just have an example. Suppose we are taking around 10 test tubes, right? And in that particular 10 test tube, we have taken equal amount of enzymes. But the substrate levels in each test tube is continuously increasing, right? Now when we will do the reaction in that particular test tube, so what will happen? Just look at this diagram. When the substrate is less, okay, so particular reaction is continuously going in increasing order because we have more enzymes and less substrate. Now but as and as the substrate level is increasing from one test tube to another, so what will happen? The particular reaction and the velocity of the particular reaction will continuously increase and increase and increase. But after a particular stage, what will happen? The amount of enzyme will start reducing, but the substrate is increased. So after that, a particular stability will occur because the enzymes are less and almost are finished and have formed their particular enzyme substrate complex, and so no further enzymes are left to bind with the substrate. And that's why this graph actually further increases in the beginning and increases, and then will come at a particular stage where it gets flattened because the enzymes are now no more to be get binded with the particular substrate. So this is the substrate concentration effect. Now our more important term, Km value. Now what is Km value? Km value is a substrate concentration at half maximal velocity. Means Km value denotes the substrate concentration at half maximum velocity. That means this is the maximum velocity. So at the half maximum velocity, whatever amount of substrate concentration we are having is the Km value. Means suppose over here we will get the Km value of this particular graph. Now it denotes that 50% of enzyme molecules are bound with the substrate molecule at a particular substrate concentration. Okay, and after that particular half velocity, there will be maximum velocity, and after that there will be a straight line. Now the Michaelis constant. According to Michaelis theory, the enzyme substrate complex is reversible process. Right. Now while the breakdown of the complex to enzyme and product is irreversible, and so it can't be get back to the substrate level. Now in this figure, as you can see in this figure, the 50% velocity in the y-axis over here, means somewhere over here, the 50% Vmax. 50% Vmax is actually corresponding to the point on the x-max where it gives a numerical value of Km. I told you before only that means half Vmax is equal to Km at the x point, at the x plot. Right. So remember, Km is independent of the enzyme. Very important. Km is independent of the enzyme concentration. So whatever amount of enzyme we will add, it will increase the Vmax. It will increase the velocity, but it will not affect the Km value. It will remain the same. So thus, irrespective of the enzyme concentration, 50% of the molecule are bound to the substrate at the particular substrate concentration level. The lesser the numerical value of Km, the more the affinity of the enzyme for substrate would be. For example, just take an example, glucokinase is actually having 10 millimole per liter of Km value, but the hexokinase has 0.05 millimole of mole per liter of the Km value. So therefore 50% molecule of hexokinase are saturated even at a lower concentration of the glucose. In other words, hexokinase has more affinity for glucose as compared to glucokinase. Why? Because its Km value is less as compared to the glucokinase. Now next is the double reciprocal plot or the LINEWEAVER-BURK equation. Now sometimes it is impractical to achieve high substrate concentration to reach the maximal velocity condition. Why? Because I told you before, only for determine the particular Km and the Vmax value of a particular reaction and the enzyme, we are taking a large amount of substrate. Okay, but what if we are not able to take a large amount of substrate every time? So half Vmax or the Km may be difficult to determine over here, right? So then the experimental data at lower concentration is plotted as reciprocals. As you can see, we will find the reciprocal of this particular data. Okay, and then we will just obtain a line extra plotted to get the reciprocal of Km. And this is known as the LINEWEAVER-BURK plot or the double reciprocal plot, which is derived from the Michaelis-Menten equation. I told you before, this is the Michaelis-Menten equation. V is equal to Vmax into S upon Km plus S. Now we will invert this. Why? Because we have taken less amount of substrate and found the reciprocal of this, and then we will continuously increase the line to get the reciprocal of this particular plot in the graph. So we will do this, and so at the end you will get the reciprocal or the double reciprocal equation, that is the 1 by velocity is equals to Km upon Vmax into substrate plus 1 upon Vmax. Now next is DIXON plot. Now what is this? This is mainly used to determine the inhibition constant. Now what we will do over here is the velocity is measured at several concentration of the inhibitor when the substrate concentration is kept constant. So by doing this, we will able to determine the inhibition constant for a particular substrate and particular enzyme and in a particular reaction. Now next is the cooperative binding. Now in this, the binding of the particular substrate to one unit enhances the affinity for binding to another subunits. Okay, but this is mainly done in the remember, for oxygen binding to hemoglobin. Okay, when one actually binds, when oxygen binds to a particular set of hemoglobin, then it actually increases the affinity for the particular hemoglobin to bind to other substrate as well. Okay, so remember, this is the diagram for it. Remember, if you remember, this is the substrate concentration diagram. This is a substrate concentration diagram. When first of all it will increase, and then it will go to a particular line, a particular point, and then it will get straight. Okay, now this is the particular curve for cooperativity. And this is the hyperbolic curve suggesting the non-cooperativity, because it may happen that sometimes after a particular substrate binds to one unit, that may not enhance the affinity for the particular binding for other substrate. So for that, this is the diagram or this is the graph. Now next is the effect of product concentration. Now in a reversible reaction, in a particular reversible reaction, when the equilibrium is reached as per the law of mass action, the reaction rate is actually lower. Why? Because when the product and substrate level are actually in equilibrium, so what will happen? The rate of reaction will get slowed down. So when the product concentration is increased, the reaction is slowed, stopped, or even reversed. So what happens in the inborn errors? In the inborn errors, as you can see, the A is converted to B by the enzyme 1, B to C by enzyme E2. But what if the enzyme E3 is not present or inhibited? So what will happen? The particular C will continuously get deposited, and so because of this, negative feedback will occur, and this will inhibit the E2 enzyme, and this particular E2 enzyme will further inhibit the formation of B, and this particular will inhibit the formation of E1, and so the whole reaction is stopped. Next is the effect of temperature. Now remember, the graph for the effect of temperature is actually bell shaped. The velocity of the particular enzyme reaction increases when the temperature of the medium is increased and reaches a maximum and then falls. Means for a particular increase in temperature, it will continuously increase, and then it will reach the maximum velocity, and after particular temperature, it will start denaturing, or the denaturization of the particular enzyme will occur, and it will go, and the graph will go particularly downwards. What is optimum temperature? The temperature at which the maximum amount of substrate is converted to the product per unit time is known as the optimum temperature. As the temperature is continuously increased, more and more molecules get activated energy. As the temperature will increase, they will get the activation energy, and as because of this, more and more molecules are continuously increasing their velocity rate, and they will collide with each other. And as because they will collide with each other, the velocity of the reaction is actually increased. Now, another very important term, that is the temperature coefficient or Q10. Now this is actually the factor by which the rate of catalysis is increased by a rise of every 10 degrees Celsius. Means at every 10 degrees Celsius rise, the particular amount of increment in the particular reaction rate is the factor, and that particular factor is actually determined by the temperature coefficient. Now generally the rate of reaction of most enzyme will double by a rise of 10 degrees Celsius. Now one more very important thing. When temperature rise is more than 50 degrees Celsius, heat denaturization and consequent loss of tertiary structure of the protein occurs in the normal human being or any normal animal. So activity of the enzyme is decreased, and as because of this you will get this descending of this graph. Okay, and so bell shape is obtained. Most human enzymes have the optimum temperature around 37 degrees Celsius. Certain bacteria living in hot spring will have enzyme with optimum temperature near around 100 degrees Celsius, and so they can be used for PCR reaction, polymerase chain reaction, because they have very high capacity for high amount of temperature. So mainly for PCR, Taq polymerase, which is produced by the Thermus aquaticus, is mainly used. Now next is the effect of pH. Now remember, each enzyme has its optimum pH range on both sides of which the velocity will drastically reduce, because for a particular enzyme we have particular pH, and so either decrement in the pH or the increment in the pH will actually cause the enzyme activity to be reduced. So the graph will show, as you can see, will be again a bell shaped and will be at the maximum at the particular pH or the perfect pH of the particular enzyme. The pH decides the charge of the amino acid residue at the active site, and the net charge of the enzyme protein would influence substrate binding and catalytic activity. The very important thing is that the enzyme's pH value actually depends on the charge of the particular amino acid present at the particular active site of the enzyme, and the total charge of the particular enzyme will actually determine and increase the binding capacity to the substrate and catalytic activity. The optimum pH may vary depending on the temperature, concentration and substrate, presence of ions, etc. Usually enzymes have the optimum pH of 6 to 8. Now remember, these are very important enzymes in our body, and the particular pH of pepsin, remember, is the around 1 to 2. For salivary amylase it is around 6, and for alkaline phosphatase it is around 9. And for acid phosphatase it is around 4 to 5. Now the enzyme activation. Now in presence of certain inorganic ions, some enzymes show higher activity. So thus, for example, chloride in the salivary amylase. Chloride actually, this ion actually increases the activity of the salivary amylase and so act as enzyme activator. Similarly with the calcium activate the lipases. Now another type of activation may be occur by this is the conversion of an inactive proenzyme or the zymogen to the active enzyme. Now over here it was just increasing or enhancing the rate of reaction, while some enzyme may also cause the activation of it from the inactive state. For example, the trypsinogen in the small intestine. Trypsinogen and all the digestive enzyme in the GIT are proenzyme beginning, and they are mainly converted into a particular mature and the activated enzyme at the end by this particular enzyme activation process. Now what happens is, by splitting of a single peptide bond and the removal of a particular small polypeptide chain from the trypsinogen, this particular trypsinogen or inactive trypsinogen is particularly converted to active trypsin by this particular enzyme activation process. Now the activated trypsin will further activate the enzymes in the small intestine, and so all the enzymes are actually activated by this mechanism. Now another example is coagulation factors. The coagulation factors are seen in the blood as zymogen form, means inactive form. So the activation pathways are also occur in the same way as that of the intestinal enzymes. Remember, these activities are mainly needed only occasionally, but when needed, a large number of molecules are to be produced instantly. So hence the cascade system of chemical amplification is done in such factors. So this is the end of part 1. We'll discuss about the further factors influencing the enzyme activity in the further next videos. So hope you did well. Thank you so much.